So polar double integrals being Jennifer's students' crux is a good segue into my talk. Title is clickbait. I'm not going to make a deep connection between multivariable calculus and partial derivatives, much as I'd like to. Instead, what I want to do is talk about the story of multivariable calculus. Or maybe, to be a bit more precise, talk about a story of multivariable calculus, because there are a lot of different stories we could tell about multivariable calculus. And I want to talk about one particular story of multivariable calculus that my students and I have been reading the last few years. And not even talk about the entirety of that story, because that would take too long, but just maybe one moment or like one episode in that story. And use that, hopefully, as a way of jumping off and talking about deeper ideas in math education. And the particular episode in that story is how we come up with polar double integrals, R, dr, d theta. So here's some context. I've been teaching multivariable calculus at the Nueva school the last few years. We're a school for smart, nerdy kids in the Bay Area. All our kids love math. They work really hard. They're really motivated. We've got year-long electives in multi and linear algebra each, plus other electives in diff-EQs, complex analysis, algebra, number theory. I haven't even listed all of those on there. I'm one of the only faculty members without a PhD. We've got a ton of freedom. We don't have APs or any of that. Pretty cool. In multi, mostly seniors and juniors, always a few 9th graders, 10th graders, probably like 2/3 of the kids overall take multi. And most of them are going off to fancy colleges and majoring in math and science and engineering. Nina's here. Nina was not in second semester multi, which is what I'm talking about in this talk, but she's representative of our wonderful, wonderful kids. As I taught the class, as I sort of figured things out, I taught it in basically a totally exploratory and inquiry-based way, not out of any particular, pedagogical program or intent, but just because that's how things seem to work best. That's how feeling out the material, feeling out the students, that's what seemed to work right, which I think is generally a good way to do things. And so in the second semester, the way I taught it, which is what I'm going to talk about here, we focus basically on integrals of scalar functions. Never get to vector calc, which is too bad, just couldn't fit it in time-wise. But curricularly, we start with line integrals and give the kids some just nice exploratory problems where they've spent all this time in single variable calc, finding the areas of two-dimensional curvy shapes. And so we ask, what if we have a two-dimensional curvy shape that's somehow curvily embedded in 3 dimensions? Can we find the area of that shape? That's the first day of class. It takes a week or so of work, and the kids, with very little guidance from me, managed to basically come up with a formulation of a line integral. How to do that. Very cool. Then we go on. We start thinking about how do we find volumes of 3-dimensional curvy shapes. We spend all this time in single variable calc talking about the areas of curvy 1D shapes, and our thought process for that is kind of, if we can find the area of a curvy 2D shape, then we've effectively found the cross-sectional area of some curvy 3D shape, so we can do a second integral and find a volume. So we do that, and we go on to polar integrals, spherical integrals, and cylindrical, spherical, whatever, surface integrals. Wrap up the semester by seeing that the determinant of the derivative matrix ties all this stuff back together and becomes kind of like a master formula for everything we've been figuring out all semester in an ad hoc way. So it's that moment that I want to talk about in this talk. And maybe before I get too deep into that, I want to describe some of the ideas that are sort of deeply in my mind as I'm thinking about teaching, as I'm thinking about math. Maybe you could call it a theoretical framework, but that seems like such a fancy word. It's that math, I think, and teaching math, which are connected, we're really just reading these stories about abstract objects. We read stories about people in literature. We read stories about 747s or westward expansion or, I don't know, protons in nonfiction. And in math, we're reading stories about abstract objects. And there are really all the same literary features. There's plot, there's subplot, there are themes, there's rising action and falling action and foreshadowing, all of that. But everything we're doing is really just a story that we're reading. I don't want to say that I'm telling it, by the way, because I think that would be me imposing too much structure on things. It's a story that we're all reading together. Maybe I've read it a bunch of times more than the kids, but it's the story we're all reading together. Kids have been using the word side quests a lot recently from video. I don't play video games, but the kids will describe stuff that I would call a subplot. They call it side quest, which I love because it just shows how deeply they're in this mode too of thinking about math as a narrative, as a story. And sort of within this genre of ways to think about math and teaching, there's sort of like two things in particular that have been on my mind a lot the last year or two. One is that one of the things we're always trying to do as math teachers, I think, is getting kids to focus on the process rather than the result. Getting kids to worry less about the answer and more about how you come up with the answer. And the phrase that I stumbled across a year or two ago, I don't know if I had this for Nina's class, but was no spoilers, which has just worked like a complete charm. Because before I came up with this phrase, I would, go on, long exhortations to the kids about the value of the process over the result, et cetera, et cetera, et cetera. And I think they sort of bought it just because they liked me, but I don't think I ever really persuaded them rhetorically. But you see no spoilers. It's a perfect analogy, and it makes it totally clear what we're trying to do. If you're reading a murder mystery, or like watching a whodunit, the point isn't really to figure out who the murderer was. That's part of the point, certainly, but it's not the whole point. If it were, then you would just skip ahead to the last 5 minutes or the last 5 pages. But you don't do that. You, in fact, watch the entire show. And I think that's true in our mathematical adventures as well. Other thing I've been thinking a lot about this year in particular is tension, narrative tension. How do we build narrative tension? How do we sustain narrative tension? If you know who the murderer is, it's very tempting to just blurt it out. You know who the bad guy was, you know how the story ends, you want to see him locked away as soon as possible. It's very tempting to just give away the ending. Not just for the kids, but for us as teachers, because we know who the killer was, we know how the story ends, and so we really want to give away the ending. And instead, one thing I've been really leaning heavily into the last year or so is really dragging things out, really building that tension, really sustaining the tension of these stories, not resolving questions too quickly, really letting things simmer and percolate. Maybe the other analogy I would make here is not to a murder mystery, but to a romance novel, like a rom-com, where in the murder mystery you don't know who the killer was. In a rom-com, you do know what's going to happen. The couple's going to get together at the end. That's pretty certain. And yet, even though you know exactly how it's going to end, you still read the romance novel, you still read the rom-com. It's about that tension, it's about that waiting, it's about that liminal space in between, which maybe relates to my second metaphor here, about 180 degrees away, which is capacitors. I always think about like the charge on two parallel plates building up that voltage between the clouds and the ground. And maybe eventually there's going to be some sort of dielectric breakdown, there's going to be a bolt of lightning that resolves things. But until that happens, really revel in and enjoy and be in that moment of the hairs in the back of your neck standing up. So these are some of the sort of narrative ideas, rhetorical ideas, poetic ideas that are very much on my mind as I'm teaching. And back to actual MVC, back to actual multi. The episode I want to talk about happens about maybe a month into our second semester, where so far we've figured out how to do line integrals, we've figured out how to do double integrals and rectangular, we've figured out how to do triple integrals to find not just 3D volumes, but 4D hypervolumes, or like a mass, or total energy, or something like that. It's really delightful. We've got this argument where we can use one integral to find the area of a cross-section, and then turn 90 degrees, and use a second integral to add them all up, get a volume, and we can just sort of iterate this process in as many dimensions as we like, and it's great. And higher integrals then are just for loops, basically. They're just lots of nested single integrals. They're just Matryoshka dolls, essentially, of single integrals. And so we're in this lovely position now where we've all got a lot of confidence and a lot of joy in figuring out that to do integrals in higher dimensions, we just want to recursively nest a lot of single integrals in one dimension. But that's not true, of course. It's very tempting. In the way I sort of set up this story for this class. It's very tempting to fall into this trap. And everyone does fall into this trap. But it's not true. So meanwhile, as we're doing this, we're doing lots of calculations, we're finding lots of volumes of various shapes, and some of these shapes have nice rectangular bases, and some of them have maybe more circular bases. One of the shapes we spend a while thinking about is this lovely pipe organ shape. I stole this from a textbook years ago, but just a cylinder with a little linear slice through it. I asked the kids to find its volume, and they do it in rectangular. They make a bunch of cross sections, through it, add up all those cross sections. It's hideous on so many levels because this is a fundamentally circular shape, and we're cutting it this way. It's like cutting a pizza like that. Why would you do that? It's disrespectful, I think, to the shape. I'm serious. I think just like in literature classes, we ask ourselves, like, how does this text want to be read? And I think in math, the equivalent is, how does this abstract object want to be understood? Or even more specifically here in multi, how does this shape want to be integrated? And this shape does not want to be integrated in rectangular. You can do it, but it certainly isn't pleasant. It doesn't look pleasant visually. Outline of the calculation looks like that. And a very simple answer, which is cool, is just an integer multiple of pi. Full calculation from one of my solution sets. You can't read this, but you don't want to. You can do it by hand. It just requires a trig substitution, if you know that. And kids all love math and are eager and hardworking, and so they will do this. I wouldn't say they would do it gladly, but they will do it. They're a little salty because they also love polar coordinates. especially if they've taken my pre-calc class. They all have polar coordinates, and so they basically all want to integrate this in polar. Not the only shape, we're finding the volumes of lots of shapes, and some of them are kind of circular, and the kid's instinct always is, right away, wouldn't this be nicer? Wouldn't this be more simple? Wouldn't this be just much more elegant if we integrated it in polar? And so for a while, I tell them not to. I say, no, just do it rectangular, trust me, and they're grudging, but they do trust me, and so it works out. We're building that tension. We're doing things the hard way so that we can really earn the easier way. We're doing things the hard way before we figure out the easier way. And then eventually, after a while, I finally say, okay, we can do it in polar now. You can figure out how to do it in polar now. And the kids, because again, I'm not telling them how to do any of these problems, I'm just posing these problems, and the kids are figuring out how to do them. The kids have basically two ways that they want to do them in polar. One way is to make these nice radial pizza slices. Use an integral to find the area of one of these radial pizza slices. You don't actually need an integral, but you can do it anyway. And then add them all up with a second integral by spinning around in a circle. Very obvious, very natural, very intuitive. And if you do that, the calculation in its outline looks like that. Convert the function to polar, do the first integral to find the area of the pizza slice, do the second integral to spin it around, and you get 30 pi. Which is not the answer they got the other way. And no calculators here involved, by the way. This is all, you can all do this by hand. So there's no worry that we're somehow offloading our brains and there's something going on with the computer. They're doing all of this by hand. So this is distressing. And there's usually a second way that kids come up with to find the volume of this shape. Instead of pizza slices, make these nice concentric crustule slices, is the one that kids call them. Charlotte Rosario. And you can do it this way. You can do one integral, a line integral, to find the area of these crustule slices. We don't have to do line integrals, so that's great. And then a second integral, slide them out, in and out on the radius to find the total volume. Calculation looks kind of like this, and we get 45 pi. Which, that's a number we've seen before, so that's good, but we still have this pretty big problem of 3 different ways of finding the same volume and 2 different answers. Which is not great. And so at this point, you know, this has taken a week or so of work. It's not the only thing we're doing, but it's the main thing we're doing. The kids have worked themselves into this paradox. It's distressing, and they have to work themselves out. And eventually, with more work, somehow, they figure out that to do a double integral in polar, we need to integrate not just with respect to dr d theta, but with respect to r dr theta. So, it's about 2 weeks of work to figure that out. Not the only thing we're doing, the main thing we're doing. And it is, I think, the sort of intellectual and emotional heart of this semester, of this class, the way I've taught it. It's, I think the moment is, in the fall semester of this class, our sort of like big, deep insight, this is when we're talking about derivatives, is that derivatives in higher dimension have a sense of direction. They don't have if you're talking about single variable calculus. And so in the fall semester, we sort of spend a long time figuring out that they've got direction, and then figuring out the implications of that. And now in the spring semester, what we're doing is sort of figuring out that integrals, that these differentials in integrals aren't just like a closed parentheses, which I think they basically are if you're in single variable calculus. Dx is just where the integral ends, and maybe also tells you, what it's with respect to. We're figuring out that differentials actually are objects in their own right. We're figuring out that higher integrals aren't just iterated single integrals, that higher integrals themselves are objects in their own right, and that just as we need to use calculus to deal with curvy shapes, use calculus to take into account their curviness. If we have a curvy coordinate system, we need to take that into account as well, which is something kids have never seen, never thought about before. And so we've spent a month, 6 weeks or so, sort of like building up to realizing that insight, and then spend the rest of the semester seeing what results from it. Semester continues, we sort of become engineers of integrals then. Spend the rest of the semester coming up with sort of more and more elaborate correction factors, differentials to calculate all sorts of integrals, all sorts of geometric quantities we might want to come up with. We do triple integrals in cylindrical and spherical. We do surface integrals and cylindrical, which is fun. Kids come up with all of these themselves, it's great, et cetera, et cetera. And then finally, at the end of the semester, we see that really everything we're doing is just taking the determinant of the derivative matrix. That's really this master formula for all this ad hoc work we figured out. Maybe this would be like the intellectual climax of the class, but by that point it's June and everyone's tired and it's time to leave the movie theater. So just real quick, I want to speed through some of the sort of the deeper ideas that I think come up here. Maybe we can talk more about in the discussion. One is, this looks really simple. It's just an R there. And I think one of the things that probably everyone in this room agrees with is that just because something looks complicated doesn't mean that it is complicated. You can have big, scary formulas. They're actually very simple conceptually. But the converse is true as well. I think just because something looks simple, just an extra R, doesn't mean that it is simple, intellectually, conceptually, and doesn't mean that it's not also worth our sort of deep time, deep attention as well. Other stuff, the kids come up with this idea of polar double integrals as r d theta, not because I've told them that that's how you do it, not because I've told them that that's how you do a polar integral and then we've proven it, which would be better. Not because we've come up with some very deep general theoretical apparatus in which the kids have proven that. Rather, we've figured it out just by thinking very specifically about a specific shape, a specific problem. It's a model organism. We care about nematodes, not because we're actually obsessed with nematodes in and of themselves, but because they're so representative of our deeper questions, our deeper ideas in biology. And so that's something I think a lot about in my teaching. How do we choose the right model organisms? I think in research, this is something we're doing all the time. We're always thinking about how do I find the right sort of specific example of this general phenomenon I'm trying to understand. But in lower level teaching, I think it's easy to miss this. Easy to forget that we need to find the right specific examples, even when we're trying to teach general phenomena. I try to be really innovative with notation. I'm always encouraging kids to like mess around and come up with their own notations. I'm always telling kids that math is not the same as notation, that notation is supposed to work for us, not the other way around. I think that's especially true in multi, which is, I don't even know how to describe it, but every textbook in multi I read seems to have a different notation, which makes it very challenging. I'm always thinking about this trade-off between being really concise in notation versus being really verbose. Advantages to being anywhere on the spectrum, but how can we sort of play around with our notation, play around with where we are on the spectrum. do that thoughtfully, intentionally. Another spectrum I'm thinking a lot about is between clarity and obscurity. A lot of times we want to be crystal clear about things in our teaching, and other times we want to be obscure. And I think there's nothing inherently good or bad about either of these extremes, as long as we're being thoughtful and intentional about where are we trying to be on this spectrum. Kids have finite resources, just like we do. They have finite time, energy, intellectual energy, emotional energy, and how do we get them to spend their finite intellectual and emotional energy on the right obscurities, not the wrong obscurities. I try to approach my teaching with a spirit of optimism, which I mean very specifically looking for what's right and what's true in the kids' work, and not trying to hunt down what's false. There's absolutely no risk here. Teaching math is not, it's not flying an airplane, it's not heart surgery. If someone gets an integral wrong, no one dies, it's not bad. And as a result, I think we need to focus on the upside, because there really is not a lot of downside. To put it maybe even more aggressively in one of these continuums, we can try to seek God, or we can try to stamp out sin. Maybe these things are both valuable, but I think St. Augustine would not like the dualism of my theology up here. I think maybe as mathematicians, often we're so focused on the details, so focused on precision, that we lose sight of the bigger picture. Maybe at the margins we need to be seeking what's true more than what's false. Lots of other cool stuff in these slides. I'll just zip through these. What are those? If you want to see, I've got them up here. What could this possibly be? Who knows? I've also got some zines if you want. I've got an actual handout for this talk, plus some zines. These zines are about complex exponentiation, not about multi, but they're pretty great. Finally, I'm on the job market, more or less, potentially, or the school market, or the something market. I have a weird academic background. I don't have a PhD or any sort of degree whatsoever. But if what I'm saying is intriguing to you at all, I'd love to get in touch. A lot more stuff on my website. Thanks, guys.
So I think we are at the end of this talk, but we have a discussion session, so maybe Alexander can take questions and we can start discussion. The purpose of this discussion session, like we have half an hour, like 9:30 to 9:30 to 10. But I think like we could have like 20 minutes discussion session and maybe take 10 minutes break and come back for the session. Yeah, so, and the idea of the session is for the audience to talk to speakers and as well as with each other. So we encourage people to come out and speak and express their ideas, opinions, like you want to agree, disagree, fight, like whatever, right? Yeah, so maybe like questions for Alexander, you could start there.
Well, so looking at the analogy of as a story, you said no spoilers, but I will say, sometimes when you accidentally see the end by accident, you still find the story interesting.
Yeah.
Because there,
Yeah.
I guess, sometimes even if there is a spoiler, sometimes the spoiler can make you wonder what the rest of it is, in the sense that when you get to the end and they say who done it, you then have some context for looking for how did we get to that? How the heck did that suddenly come out of there? And as you go back to it, you have a different perspective on what you're looking for. You're looking for things that tie into it that may not have been obvious initially. So sometimes knowing the end of it can work in a different way as well, I guess is what it's.
I agree. No, I agree entirely. I think how I would phrase that in this way is we don't need to read stories entirely linearly, right?
Yeah.
We can have the cold open with the the ending and then the whatever.
Yeah.
Yeah. No, I agree entirely.
I mean, as I guess an example, I accidentally took one of the calculus series twice by confusing semesters with quarters, but it was interesting going back the second time because I could look at very different things that I wasn't able to look at the first time because I had the end perspective and I could focus on, okay, here's the interesting things I never had time to really look at because I was trying to work through it at the beginning.
So just like when we're telling like other types of stories, we want to play around with like the chronology, right? How
Yeah.
does the chronology of how we're writing the story maybe not match the chronology of, you know, the actual events, right?
Yeah.
And playing around with that structure, that like non-linearity, that non-whatever.
Yeah.
Yeah.
But yeah, so I guess sometimes having a spoiler doesn't necessarily hurt. I suppose probably you have to get the spoiler carefully so that
Yeah, thoughtfully and intentionally, yeah.
it leaves the questions still there, I guess,
Exactly,
is
yeah.
probably the kind of spoiler that you would want to give.
Yeah, yeah.
I know.
Can you say a bit more about the testimony?
This was a project, I do a lot of stuff in my classes that is fun, but maybe not intellectually all that meaty, but this was fun. This is a project I did with my student Ethan Kim a few years ago. I've got them here. Where on the day his class was trying to figure out the correction factor, that's what I call it, the correction factor for spherical triple integrals. Basically what I did was say, figure out the correction factor. Kids had heard of spherical, they had some sense of like spherical coordinates, and so we talked briefly about how, okay, an infinitesimal element in spherical is going to be a little wedge like that. I drew a doodle on the board, find its infinitesimal volume. So that's what I did. And Ethan, who's the robotics, who was at that point the robotics CAD team lead, he's now studying Mackie at Princeton, turned to CAD instinctively just to like make a spherical wedge in CAD just because, I don't know, it's a place to start. And I saw it and was immediately excited. I was like, oh my God, we need to 3D print this. And then metastasized into this like much larger project, which was kind of my vision, and I turned poor Ethan into my CAD person. This was the whole vision as it evolved of these like, 5 different interlocking, infinitely small Lego pieces. Ethan spent so much time in CAD as a like spring semester senior who already was way too burned out, and I felt kind of bad, but not that bad. Yeah, that was that project. It's cute. How educational is it? I don't know, but it's very cute and they're fun. I got something from Ethan at the very end. It was never all that clean, and I've been harassing him about this for so many months. I have various versions of STL files, which I mean to put on Thingiverse or something like that. But I'll turn out.
How do you play with these?
Well, you can take them and snap them together. I've got a cylindrical one right here and a spherical one, and you can put it on, and these ones actually fit.
Oh.
And I don't know what mathematical insight you're getting from this, but it's kind of fun. We've got a rectangular one too. Art.
Okay.
Yeah, we can put a 2D one. Yeah, it's cute and not particularly meaningful, but entertaining.
Thank you. I think that's cute and entertaining.
This is a question for both Andrew and is Ethan still here? I'm trying to, maybe not. So maybe just Andrew. Like your approach is clearly centering the student experience of all these topics, which is really wonderful. And I am noticing a difference in how you and Lisa were talking about what's actually happening in the classroom. And I was wondering if you could, if you had any thoughts about the interaction between these ideas. What I'm noticing is, Lisa pointing out that humanistic mathematics is about prioritizing the human student over, or learner or teacher or mathematician in general, over the divine supernatural mathematics. And then at the same time, one of the things that you're describing doing is asking your students to wonder how the abstract object wants to be understood, which on the face of it sounds like prioritizing the divine supernatural mathematics over the human. And so I'm wondering.
I really wish I did not see Lisa's talk.
Oh,
I wanted
I'm so
to-
sorry.
No, I wanted to, but I got lost, and now you just made me even more bummed that I missed it, because the way you're describing it sounds so thrilling.
Everything is being recorded, don't worry.
Well, that's right, but I can't watch the recording in the next
We'll
5
share
seconds.
when.
Yeah, I mean, I think maybe the response I would give is that, we're prioritizing both. We're prioritizing sort of the I don't know, maybe we could do another voltage tension explanation. We're prioritizing students coming to the best understanding of this abstract divine world. Maybe that does mean prioritizing the abstract divine world, in which case I think I'm okay with that. I think I'm okay with asserting that actually we're, as human beings, we are not ourselves divine or immortal, and part of our process of being people is to sort of submit to the external, in a sense, not to get too deep into the theology there. It doesn't have to be harsh or cruel, but to realize that we're sort of all at the under the purview of math. One of the things I often say in my classes is how I'm not in charge of the class. It's the math that's in charge. All of us are sort of subject to the math, me included. I don't know, I feel there's a lengthy, deep answer I could give. Is that, I don't know, what's your response to that?
I'm just interested in what take you had in your
I don't know, if we're prioritizing humans, I don't know, math is hard. I think math is hard, and maybe I would ask, we wouldn't do math at all. A lot of people, not everyone, most of the people in this room probably still do math, but I love that as a question.
I think this is a topic very central to the group of us that are organizing this. So I invite us to linger on it if you guys are interested in terms of the juxtaposition between the human aspect of math and then the aspect of math that just exists there that we're
Divine
exploring.
aspect.
Right? There's a duality there that we don't want to erase, but we want to foreground. So
We have maybe a comment here.
I enjoyed your talk a lot, and I think teachers like you really provide a foundation. I'm wondering if you or your students ever go on to kind of transgressive textbooks. Here I have in mind Michael Spivak's books on geometry, and also William Burke's unfinished text but widely circulated called "Div Grad Curl Are Dead." Do you know do these works, and do your students ever go on to read them? Because there's a lot of commonality.
I don't know Div Grad Curl are dead. I know Spivak's calculus, because I use that. I know
Yes,
Spivak's
Spivak's
geometry.
calculus, he's the one where he said definition should be, theorem should be easy because the definitions are hard.
Yeah, that's a great question. I don't know. I've never heard of that.
Look up Div Grad Curl Are Dead. You can find copies online. He died shortly before finishing it, but the galley proofs are out there. And this is a famous book among engineers.
So thank you for the talk, and especially the insight that we're telling stories about abstract objects and sharing that, because the first time that I was turned on to that idea was reading Charles Pinter's book on abstract algebra, and he tells a story, and there's a section where he says, all these streams are coming together, and now we're going to form this river that, and the big insight, this climax is going to occur in this next chapter. And I remember reading that and just having one of those moments of realization that this is how math is told as a story, and so I appreciate you sharing that. And the question related to that is, stories are such an important part of our human way of understanding things. Are there any other forms of media or any other representations, maybe set aside visual, because I see you're using visual, but any other thoughts that you have about what sort of media helps humans understand mathematics?
Thanks for the example from Intro. I didn't know that, but that's great. I was really thinking a lot of my classes about having these, multiple parallel streams going together. And in my pre-calc class a couple of years ago, this is a very intentional thing of having two different streams that seemed to the students very distinct, and then converge like the last day of class, and it was thrilling for everyone. As to other forms of media for doing math, yeah, I love that question. I'm a writer, so this is how I think about it, and that's sort of all I can do. Yeah, I think so much great intellectual work comes in the, tying together of two different media, like maybe writing and math. I think of my favorite contemporary novel is A River Runs Through It, and that's very much a novel about sort of words and fly fishing working together in these two very different artistic media, words and fly fishing, and sort of how do you sort of go between those two media. So I think as an intellectual process act in general, that tension, that voltage, that whatever between two distinct fields is very exciting and powerful, and lots of insightful bridges in both directions when you're making those maps.
Yeah, please.
Sorry, a somewhat related question is, I think different people, they might have different favorite approach or favorite media. Like in my class, some students, they are really good at abstract thinking in terms of symbols and notations. Or some people are more like literature or story oriented. If you have observed that in your class, or if there's ways to modulate the class to different kind of people, to tailor it to their own favorite way of acquisition of knowledge.
Yeah. And I think at the margins, sure. I think maybe the sort of gentle pushback I would give is that I think on the one hand, we do want to sort of adapt to each individual student's strengths and weaknesses, not try to force people into the wrong boxes. Try to look for what's good in their work, not what's wrong, as well as in their working style and their working medium. So I agree with that as far as it goes. On the other hand, I think maybe the counter argument there could be that I don't think any individual's teaching style is going to work for any student. That's fine. What's the sort of best what's the best version of yourself as a teacher that you can be? And I think that's usually a better approach than to try to sort of be all things for all people. I think trying to be all things for all people is usually a recipe for failure, versus saying, what's the sort of best version of my teaching for this class? For some students, maybe that's not going to work out. For my students, it seems to be a pretty high percentage, so I'm okay with that, but it's never going to be 100. Yeah, trying to be all things for all people, I think that is I would call that a failure mode in teaching, and it's one that I see a lot.
I want to return to the distinction that's being made between the human and the divine, and sort of give a different framing for that, because I think we shouldn't, it's dangerous to identify, this resonates with what you were saying, dangerous to identify the human with the individual, because there are other levels of human. There's cultures, there's groups. The class, your class as a group is something which is not just the people in it. And so I think maybe we could, that then brings the mathematics back into a form of the human, because it's in the communication and the agreement that can exist. And I think one of the interesting things about the mathematics that survives is the mathematics that a lot of people agree about. So instead of thinking about it as divine, thinking about that thing that can be seeking the, mathematics is that seeking the good, it's seeking the agreement that we can all have as a group. Or at least a large number of people.
I agree so heavily, and I want to just like piggyback on that and say, one of the things I'm also always trying to accomplish in my classes, I think successfully, is to make the point that as a class, we're not just a bunch of individuals learning mathematics separately. We're a team. I make all these team metaphors, which is weird because I don't know anything about sports. I actually got really into watching like sports movies for a while, and it's sort of like research here. I was like watching these like football movies where there's like the inspiring coach and the team that comes together and taking notes. This is not my culture at all. But we're a team, right? And it's there's a sense in which we're learning math not individually but collectively, and that's what matters. I think that's especially true in these sort of exploratory environments, where I think about, is everyone in the class going to be able to figure out on their own the, surface area, the differential surface element in cylindrical? Absolutely not. And if I had them do that, it would be a disaster. But you just need to have like one person figure it out, and then it sort of virally spreads, or even more so, a couple people working together can figure it out, and working together, you can have more than one brain, and collectively the sort of not the sum, but the network brain of the entire class is a lot more than any one individual, even the smartest kid in the class.
I wonder how to grade students, like, in this exploratory cooperative environment, like.
We have pass-fail grades in Nueva. Pass is an A. Everyone passes. That sounds a little cynical. I don't want to say that. It's a small environment. Kids turn in problem sets twice a week for the class. We have 2 class meetings a week. Slide. And I read them closely and give them close comments, and everyone is working extremely hard and learning all the material, and so I'm very comfortable giving everyone an A. Second semester, there's usually 1 or 2 seniors who are checked out, and so they get a B, occasionally a C, and that's fine too.
The point of education should not be like pattern, right? It's like helping the students to find what they really care about, right?
And because, if we were having to do this at scale with like 100 kids, we couldn't do that, but with 2 classes of 15 kids, it's totally.
I was also wondering how sustainable, or like, it's not really sustainable, is not the right word. Like, how can we bring this exploratory environment to, like, in every school, right? And what are the resources that would take? Like, this is possible because that's a special school, and like, you are given the freedom to explore teaching and to bring your character into teaching, right? But not every school has that. I was wondering like how to do that.
I wonder that too. I have a lot of optimism at the local level about teaching, and I don't have pessimism, but doing things like this at scale is hard. It's countercultural.
One question that I asked in another seminar actually comes from Poincaré, who wrote, there are novels that to a mathematician are worth 100 books of geometry. So I'm curious what novels your kids are reading, in which, if they're reading any in these dismal times, but I'll bet that some of them are reading novels that in which they find sources of hope and inspiration. And you already named A River Ran Through It. Any more novels that you or your kids could name would be helpful to me.
Nina, what novels were you reading in high school?
Oh, in high school, let's see. I was reading, I think, okay, senior year of high school, I think my favorite novel I read was, well, the 2 Joseph Conrad, like, political novels, like, Under Western Eyes and wait, what's the name of the other one? I forget. And then junior year of high school, I can't quite remember. I really liked Borges's stories, but I can't remember like which full-length novel I was my favorite. I don't know.
I think that's my answer. Former student at least.
You also do plays, you have them read plays in class as
Oh, yeah, that's
well.
right. I've ended multi the last 2 years with a table read of a play. We did Proof one year and Arcadia last year.